Hello everyone, and welcome to chapter 11. We will be discussing the chi-square distribution. This is one of our final new distributions of the semester. So in the first section here, we're just going to be introducing kind of what it is, look at some brief facts about it, and then we'll be moving on to the different types of testing that we can do with it. So the chi-square distribution is abbreviated with this symbol. It looks like an X, but it's a Greek letter chi. So basically, you just picture like an X, but with kind of a swirl through one side of it. And then we put the square on there to represent just chi squared. And then the degrees of freedom for this depends on the way that it's being used. So we're going to see some different tests throughout the chapter, and each test may have a different way that we compute those degrees of freedom. So just some brief facts about the chi-square distribution. Chi-squared is a continuous random variable. The shape depends on the degrees of freedom, just like the t-distribution, so it can change as you have more or fewer in your sample size. All values are non-negative. The mean of the chi-square distribution is actually the degrees of freedom, and the standard deviation is given by that formula. A lot of this stuff is just kind of intro information, and you'll see kind of in the next sections how we're going to really be using it. It is skewed right, so if you remember when we talk about the skew, that means that most of the data is on the left side of the distribution, and then the mean is just to the right of the peak, and then as the number of degrees of freedom increases, the distribution becomes more nearly symmetric. So we can see down here, we have an example of the chi-square distribution. You can see it kind of has this shape where the curve, the highest point, the peak, is over here on the left for the most part. And then as the degrees of freedom increase, you can see this peak is moving further and further to the right. So if we had a really, really high degrees of freedom, it would look something more like that, where it looks more symmetric, almost looks like a normal curve if you push it over far enough. So this is the chi-square distribution. We're going to be using the technology in order to find the information that we need. I'll be showing you how to do that in the next section. So that's it for 11.1. So it's just a really quick introduction into the chi-square distribution. So let's go ahead and move on and see what we can do with this. So in 11.2, we're looking at a goodness of fit test. So in the goodness of fit test, we're determining whether a discrete categorical random variable matches a predetermined expected distribution. So we have this idea that we are expecting something to be distributed a particular way, and we're trying to determine whether the data that we got matches what we expect, if it's a good fit to the distribution that we expect or not. So the first thing we need to look at is the concept of an expected count. So if we're trying to determine whether our distribution is a good fit for what we expect, we need to figure out what do we expect out of these data samples here. So suppose that there are n independent trials of an experiment with at least 3 mutually exclusive possible outcomes. Okay, because if we only had 2 possible outcomes, then we're looking at a binomial experiment, potentially. We have P1 is the probability of observing the first outcome, which is E1. The probability P2 of observing the second outcome, E2. And then so on and so forth. So every outcome that we could possibly have has a corresponding probability, the likelihood that that particular event will happen. And so the expected count for each of these outcomes is going to be given by n times p sub i. Okay, so we take the total number and then multiply that by the probability that this event will occur, and we denote that using E sub I. So to see what this looks like, let's look at this example down here. A sociologist wishes to determine whether the distribution for the number of years caregiving grandparents are responsible for their grandchildren is different today than it was in 2000. According to the U.S. Census Bureau, in 2000, 22.8% of grandparents have been responsible for their grandchildren for less than 1 year. 23.9% have been responsible for 1 or 2 years. 17.6% have been responsible for them 3 or 4 years. 35.7% have been responsible for 5 or more years. The sociologist randomly selects 1,000 caregiving grandparents, compute the expected number within each category, assuming that the distribution has not changed from 2000. So here we are assuming that what we expect is actually going to happen. We expect that the distribution has not changed over the years. So we're going to use these numbers. And then when we get to the hypothesis testing, we'll see whether or not it might have actually changed. So in order to get the expected counts, so we're going to have, this will be, let's see, less than 1 year, we'll call that outcome 1. 1 or 2 years will be outcome 2. 3 or 4 years is outcome 3. And then 5 or more years is outcome 4. So we're going to have E1. So if we have a sample of 1,000 caregiving grandparents, we take 1,000 times the probability that it's less than 1 year. That probability is 0.228, right, corresponding to 22.8%. Multiply those two numbers. That gives us 228. So, and if you think about what a percentage means, right, this just means that if we're expecting 22.8% of them to fall in this category, and we have 1,000, then we're expecting 228 out of the 1,000 to fall into that category. Similarly, for the second one, we have 1,000 participants. The probability of being 1 or 2 years is 23.9%, so that's 0.239. When you multiply, gives us 239. The third outcome, the probability of it being 3 or 4 years is 0.176. So we get 176 that we expect in that category. And then the last one, we have 1,000 in our sample, and the probability is 0.357. So we would expect 357 of these grandparents to be in the category of 5 or more years, based on the data that we have from 2000. Then, if we look at how we're going to use these expected counts to run a hypothesis test, how do we determine whether our data does fit well or is a good fit to this distribution from the past? So we're going to let O sub I represent observed counts. So when we say observed, we're talking about in our study, we observe these particular counts. And then E sub I represents the expected counts. So that's the ones that we were just talking about. K is the number of categories. And N represents the number of independent trials of the experiment. So in order to determine our test statistic for chi-squared, we're going to be taking the sum of these terms. So this is the observed minus expected squared all over the expected. Okay. And we would need to do that for each I. Okay, so if, like in the last case, we had 4 different categories, there would be 4 terms that we would be adding up together, and then we just do that for however many there are. So this is going to approximately follow the chi-square distribution with k minus 1 degrees of freedom. So that's just take the number of categories and subtract 1. And this is provided that all the expected frequencies are greater than or equal to 1, and no more than 20% of the expected frequencies are less than 5. Because if all of your expected frequencies are really small, then we run into trouble where the data might be a little too sensitive for the test, and then we're not going to get reliable information. So this is the formula that's going to help us here. So here's kind of our breakdown of how to run the goodness of fit test. So establish the null and alternative hypotheses. For a goodness of fit test, it actually works out pretty well in our favor because they're going to be the same every time for a goodness of fit test. The null hypothesis is that the random variable does follow a certain distribution. This is what we expect, right? The expectation is that it follows the same distribution that we saw before. The alternative hypothesis is that the random variable does not follow that distribution. Okay, so our alternative is that it doesn't go with what we expect. Then we decide a level of significance for alpha, and then in the next step, this is where we compute the test statistic. So all of the stuff up in the top is just the criteria for doing this, but again, it comes down to this more formulaic approach. So we'll need to have the observed values and the expected values, and then crunch a few numbers. But luckily we can use the technology to make this go faster so we don't have to do it all by hand, because that would take a long time. And then if we're approaching it using the p-value, we're going to be doing this using technology, and I'll show you what we're going to do for that. And then we're going to make our conclusion. So that's when we determine whether we reject or do not reject the null hypothesis. So let's go ahead and look at an example. If you're doing this on a TA8384, these are the calculator steps to do it. I'm going to show you how we do it on Desmos. I think it's going to be a lot faster that way. So we're piggybacking off of the previous example where we did the expected values for grandparents who are raising their grandchildren. So the sociologist wishes to determine whether the distribution for the number of years that grandparents are responsible for their grandchildren is different today than it was in 2000. And they randomly select 1,000 caregiving grandparents, and then they got this data table. And we want to test the claim that the distribution is different today than it was in 2000 at the 0.05 level of significance. So the first thing that we can do, like we do with every hypothesis test, is just establish the null and the alternative, which again for a goodness of fit test is going to be the same every time. So the null is that the distribution is the same, and the alternative is that the distribution is different. So nice kind of simple setup there. And what we have, we need the observed values and the expected values. We have both of them here. So the observed values, this is what the sociologists got in their study. The expected values, these are the ones that we calculated based on the 2000 data. So in order to get the test statistic, we're going to get, so we have chi-squared sub 0. It's going to be observed minus expected squared all over expected. So for our first category, for less than 1 year, it's observed minus expected. So 252 minus 228 squared all over expected, which is 228. And then plus the next one. So observed is 255. Minus expected is 239 squared over expected, which is 239. And then just kind of go through these last two kind of quickly here. It's the same thing just for each category. All right. And this is definitely work for a calculator or Desmos or some graphing software. And we will find that this number is approximately 6.6046. So we have our test statistic that we're going to run the hypothesis test with. We know that our alpha value is 0.05, and we know that our degrees of freedom is going to be the number of categories minus 1. So our degrees of freedom is going to be 4 minus 1, which is 3. Okay, so we're going to need that. Now, when it comes to doing this on Desmos, we have a page on Desmos that will be on your Canvas page that you'll have access to, because unfortunately Desmos, as of the making of this video, does not yet have a chi-square capability within it. But luckily there have been many people that have created the chi-square distribution on Desmos, and we get to kind of revel in their success and use their work to be able to determine this. So I've already set this one up for us. But again, you'll have access to this in Canvas, and I encourage you just to go straight to that link. You don't need to like play around with it or try to find it on the internet. Just go straight to the link in Canvas and you'll find this. You've got a couple of sliders here that you can mess with. So there's the degrees of freedom that you can change, and you can see how the curve kind of changes as we do that. Kind of interesting to look at. But degrees of freedom in this problem is 3. And then if you put in the chi-square value right here, which I already did, 6.6046, and you can see down here on the curve, it gives us the area to the right of that corresponds to the point that we plugged in, and that little area, the p-value, is going to be 0.085627. Okay, so that is approximately 0.0856. So our p-value is approximately 0.0856. Compare that to alpha. So this is greater than alpha, which is 0.05. So, since our p-value is greater than alpha, that means that we do not have sufficient evidence to reject the null hypothesis. So we'll say we fail to reject null hypothesis. And then we can draw a conclusion and just try to keep it within the context, so we can say there is not sufficient evidence to conclude that the distribution is different today than it was in 2000. Because remember, the assumption, the expectation is that the distribution will be the same, and we're trying to show that we have enough evidence to say that it's different. But that was not the case, okay? Because we fail to reject, we say that there is not enough evidence to conclude that they're different. So we have to just stick with our assumption that the distribution is the same as it was back in 2000. So that wraps up section 11.2. When we come back in section 11.3, we will be looking at another test that we're able to use the chi-square distribution for. So we will talk about that soon.